Error budget. Reflectance is dominant. So in our error budget that I went through yesterday, pointed out that the reflectance is the biggest error source. Reflectance errors dominate. When you see two charts right in a row with basically the same title, usually it means either it means that your lecturer does not know what is happening, or they want to make a point. The fact that I'm stopping and pointing this out means that I'm trying to make a point. So guess what the most dominant source of uncertainty in the reflectance-based methodology is? You can say it out loud.
Human.
Oh, no. The dominant source. The dominant error source.
Reflectance.
Reflectance. The reflectance is the dominant error source. Now, follow-up, and what I was getting my answers, and they're good answers, and they're all valid answers, is in the measurement of reflectance, what's the dominant error source? But step one is, I'm really trying to emphasize, reflectance is the dominant error. Your measurement of reflectance is the dominant error. And that's because of the test sites we've chosen. We have these bright sites, and because we have these bright sites, most of our uncertainty at the top of the atmosphere radiance prediction is from the brightness of that site. It's from the reflectance. Reflectance errors dominate. Reflectance is dominant. Okay? So in the error budget, I go and I'm just showing again the same chart that I showed before and remind you, this 2.5% total uncertainty that we have. 2.2% of it comes from what? Measurement of reflectance. Reflectance errors dominate. The reflectance uncertainty is the dominant error source. So 2.5% uncertainty. 2.2% of it comes from surface reflectance measurements, reflectance uncertainty. Guess what the one thing I want you to walk away from the training course is on reflectance-based calibration? Make sure you get the reflectance problem. You know, that's the reflectance uncertainty is your driving uncertainty. So built into that, so what I'm going to do now is I'm going to pull out the two red ones, the Lambertian, the non-Lambertian, and the ground reflectance measurements. So in the ground reflectance measurements, we basically have three pieces here. The reference panel bidirectional reflectance calibration, the diffuse field correction, and the measurement errors. This reference panel bidirectional reflectance factor, I'll talk a little bit more about it, but this is based on somebody at the University of Arizona going through and computing all of the things that go into the calibration of the reference panel. The PTFE reference coming from NIST, the operation of the radiometer in the black lab, the operation of the lamp in the black lab, the spectral stability of all the instruments in the laboratory. All of that was done in an excellent way to get a true error budget of 2.0%, and that's been validated through round-robin experiments. The diffuse field correction has a dash in it. That goes back to that last few images I was showing about how we looked at the diffuse light. And if I pick my bands properly and I go mid-visible part of the spectrum, this is a negligible problem. I create an uncertainty if I try to correct it. So I'm going to uncorrect it, and it's negligible in that regard. The measurement errors, we'll talk a little bit more about it, but this is basically the sampling. It's what happens at the panel. The person is wobbling, they faint, the sky conditions are changing, all of that. And I'm going to make that a 1% number. So the traceability, this is a true error. So some of the stuff we've been talking about, their sensitivity analyses, their uncertainties that are relative. This is an absolute uncertainty, and it's traceable to NIST through that pressed polytetrafluoroethylene, that powdered material. The accuracy, 2% in reflectance, that's 0.01 reflectance units at 0.5 reflectance. So just to give you an idea of scale. The accuracy has been compared to other groups, both metrology groups and other people doing these types of measurements. The precision also could be 2% because it's reflectance, but we'll call this an absolute uncertainty. The reference panel itself can be calibrated 1%, but then there's some other things that end up in there in terms of instrumental effects, sampling effects, and atmospheric influences when you use that. And that goes into the other uncertainty. It goes into the measurement uncertainty, not in the panel reference. Problem is relatively easy because you have a homogeneous in terms of when we go out to the test sites. So if you're dealing with somebody who's doing validation, and they're doing validation of NDVI or some other, their life is miserable. They're talking about vegetated sites, they've got trees they've got to get above. We have it easy, and yet we're still struggling to find all of the sampling problems, the atmospheric scattering problems. But what we're trying to do is basically figure out what's happening to the instrumentation, figure out how the measurements are happening, but it really is looking at the sensitivity analysis at some point to figure out what you think your uncertainties are in terms of characterizing the reflectance. This is now getting into that measurement part. So the sampling, that's a portion of it. Spatial imagery is used to evaluate this. So we went through the process, and this is what I was telling you about, is we can look at this at a high resolution and pick out and basically grab every sample that's in there, and then we can grab a portion of those samples and find out how representative those portions are to the full test set. We can do the same thing with the ASD measurements that are walking along this path. We can look at all 15,000 of them, or we can pull out 100 or so of them. And when you start to downsample and subsample, you find that basically you can do it better than 3% by not having that full sample, but only having a few, 3 or 4 data points. And that's because even though this is heterogeneous, it's randomly heterogeneous. And that helps. So you can basically go anywhere and pick. The problem is we're not very good at picking 4 random locations. The way you'd have to do it is use a GPS random number generator and then have to go out and find those spots. Instrumental effects. Again, we talked a little bit just a bit ago in terms of the panel itself, how it gets set up, the ASD, how well it's operating, did it get warmed up properly, whether or not you're staying the same way looking at the panel, whether or not you're staying the same way looking at the ground. All of those things tend to rack up to about 1% when you start taking into account. And this is based on looking at all those data sets collected over all that time and kind of doing averages of relative changes. And that's where that 1% number came from. The other one, the non-Lambertian ground characteristics. We had that BRDF camera. And what we did was we retrieved a BRDF for our test sites, White Sands, Railroad Valley, Ivanpah, Wyatt. This was the simplistic model we got in terms of scattering angle. Scattering angle is the view angle relative to the sun. So as you change the sun angle, things just kind of move with it. But it's a nice, straightforward, simple way to model the surfaces that we had. And it's fairly good in that regard. Lambertian is flat. So this is what we put into the rate of transfer code, and then we put in the real model into the rate of transfer code, and then we perturbed it as well, and started changing it by 10%. So instead of it being this shape, it was randomly perturbed, and what we did was really just moved it up and down and maximized, kind of twisted it and did this and so forth. And in one case, basically, you can now go to a short wavelength, 400 nanometers, a long wavelength, 800 nanometers, typical aerosol conditions, unit parameter 3.0, optical thickness 0.04 at 550 nanometers. Again, typical for the surface here. This was for Railroad Valley. And the view angle, 45 degrees, and a solar zenith of 20. So summertime, which is usually when we collect data, and the view angle is still pretty large. We normally do nadir view systems. This was worst case scenario when we did the runs, surprisingly. The 20-degree case, solar zenith was fairly severe. But even in that situation, with that 10% uncertainty, we still only ended up with in this particular case, out of high reflectance of 0.5, we ended up with a 4% effect. But when you point out that at the short wavelengths, the reflectance of the surface is smaller, it's more like 0.2, now you're down to a 2% effect. And when you run it for cases where it's not a 45-degree angle, basically the sensitivity study shows that this becomes negligible. So I have this graph here because it shows a real result, but we had to go to some very severe conditions in order to get something that wasn't negligible. So for the typical situations, for the typical atmospheres at the typical sites, the non-Lambertian nature of the surface impacting on the diffuse field to give a change in top of atmosphere radiance is negligible. So we can stay with a Lambertian surface without any problem. It just simplifies our measurements. Improving the accuracy. So what can we do to make things better? The weakest link right now is the reference and the operator. So that's where we got to fix things. More frequent measurements would help, but that would mean you have to move things with it. An 18-inch panel probably isn't the best way to do that. So finding an alternate way to do things would help. Foot traffic on the site could be an issue, especially at railroad. Spatial inhomogeneity in the reference becomes a factor. So what you really want to do is basically find a way to look at the same place of the panel all the time. And you start thinking about, well, now I need a mount to put the radiometer into, and that solves that problem. The person leveling the panel, you want to have something that might be more automated, that now it's not reliant on somebody actually leveling the panel. These actually got borne out at a cross-calibration campaign in Tuscaloosa. The CEOS group, Committee on Earth Observing Satellites, gathers a bunch of different international groups in one place. It's a salt playa in Turkey, and everybody that was there was basically measuring reflectance, and it was a comparison of the results. The goal was not to basically get everyone to get the same answer. The goal was to get everyone to use good practice. This has been done in the past. Upper left was one of the early campaigns with the Astor Group, and had several colleagues from Japan come in. Prior to that, we had groups coming in from Canada, Japan, doing work at Railroad Valley and Ivanpah, or at Lunar Lake Playa. And then we had the Tuscaloosa work. And basically, it's doing comparisons and trying to see if people are out there measuring the same place at the same time, what's the cause of the differences. So in terms of the lessons we learned from the most recent one, the 2 to 3% requirement that we're trying to get, you have to have error budgets. So now you know why we want to do this training course. Trying to get people to do good error budgets allows you to get to this 2 to 3% level. We also want to try and force people to do SI traceability. A recommendation. So a standardized format for easier comparisons. So this goes to the heart of all the people within IEEE who have been saying for many, many years that, folks, you guys really ought to have a standardized way of reporting your results, because that would make things work better to compare different people. We'll get there eventually. It's now a recommendation. Let's see if we follow through on it. One thing that we found was that everybody was using the PTFE. And some people were using it in ways that I'm probably not real happy with, and in ways that are difficult to reproduce. In this case, though, what they had was they had a laser pointer. They knew the field of view, so they could get the system highlighted here. They would level it in place, and then have the laser pointer make sure that they were looking at the center of the panel, and they knew their field of view was appropriate. This is kind of the wave of the future in terms of trying to do proper reflectance measurements. That you do a reference, then you pull the reference away, you have the site, put the reference back if you want to, or you pick it up and move to the next location. Since we only really need to sample 10 or 15 data points, this becomes very feasible, and it's a good way to make sure that everything's pointed down, people aren't in the way, you minimize the features from the measurement approach. So it's a nice way to try and get to a more consistent as well as a best practice for SI traceability.
Can I ask a question?
Sure.
If we do that approach, Will you disturb the ground that you're measuring? So you actually not even put the panel, which is very heavy,
Their panel has
legs,
a few little legs that just got it up a bit, yeah.
different level.
They also, when, for this particular site, what they were doing is they were slightly moving the tripod. So they would just pick it up and move it about 8 inches to get it away from the panel. The trick is you have to make sure that when you set all of it up, that you're not stepping here and there. You're leaving something alone.
Would an attachment, say, to the tripod, basically, where you could have the sample on a shelf that you slide in and out, maybe a few centimeters above the ground, so that way you slide it in, it's there, slide it out, you get the grounds.
So one of the groups that has done work in the past is a JPL group. They had a bicycle thing, and the guy basically had a thing where he swung the panel out the front. And, you know, so that you can do that, yeah. And then it's just a matter of, you know, buying a tripod here that's a really good tripod, 500 US. Paying somebody to build something for you to do that is, now it's a bigger effort, and so we're field people to begin with. That's the other thing you have to keep in mind is you're dealing with folks that are used to just going out and being all dirty and grainy. Let's see, PTFE white records. Say again?
That's geologist.
Yeah, well, it's,
Yeah.
field people are that way. The logistics determine how you collect, and you know there are some better ways to do panel measurements than others. And then this device was nice because it allowed them to easily see that they were level, and at the same time they could get it a little bit higher. And the perspective here, you don't see that it's quite a bit away from the body, and so you don't have a lot of influence there. Another recommendation that came in was that the use of a standardized radiometer would be a link. So instead of it being just the reference panels, actually going in and having true absolute accuracy with radiometric measurements. Processing. The largest type B error was the hemispheric directional reflectance. So when we did the comparisons, there were 8 groups. 7 groups all agreed to better than 2%. One group was off by 14%. The one group that was off by 14% was the group that was using bidirectional reflectance. So if we had chosen to basically make everyone agree, we would have purposely biased by 12%. But by understanding what best practice was, we told all the other groups that you guys are off, you people are off by 12%, and you need to improve your methodologies to get rid of that bias. Lookup table for BRF. Somehow, bidirectional reflectance factor for your specific panel, for the specific geometry, has to be taken into account some way, somehow. And again, that's a type B error. It's a bias that you're going to create if you do not do that. The sampling, and to improve the method so that we understand the sampling is the dominant differences in how you collect data. We talked a bit about how you walk the test site. Perform repeatability measurements. So this is what's nice was this was prior to us implementing the gray panel, but the gray panel was implemented because we were basically trying to assess these types of instrument measurement uncertainties. And this came out of the Tuscaloosa work as well, that not only do you want to have measurements of your white reference for a reflectance calibration, but you want to have measurements of something else that allows you to assess how much your instrumentation is changing over short time periods. What's the noise of your instrument?